Okay, welcome back to our course in quantum mechanics for computational and quantitative biology. Um, this is a short lecture, and it's basically an extension of the previous lectures where we studied the infinite square well problems in all sorts of great details. And, and it's just a lecture devoted to the multidimensional generalization to what we did in 1D. So we say now particle in a square box. So in this case, it's 2D, not just 1D. So, you know, the situation we want to model now is when we have like L, X, sorry, that's Ly, and maybe Lx, two different sizes, and the particle is confined within this system. Well, once again, this now, the Schrodinger equation, the stationary Schrodinger equation we want to solve now is a stationary equation that contains two partial derivatives, one with respect to x squared and one with respect to y squared. Also, the potential in general depends on x and y. And the wave function we want to look at depends on x and y. And the energy, of course, is a constant, so it doesn't depend on anything. So that's the kind of problem we want to solve in general. It's a two-dimensional Schrodinger equation. But remember, the rule of the game for the infinite wall box in 1D was to get rid of the potential altogether and account from the fact that we have a potential in just the boundary condition of the wave function. So that's how we solve the two-dimensional double world, the one-dimensional double world problem. And that's the same strategy we want to use to solve the two-dimensional double world. So phi will have boundary conditions, which will reflect the fact that there is an infinite energy barrier. Now, in order to solve this problem, and the reason I bring about this problem is that this equation is particularly simple in its structure because it basically amounts to two equations in one. What do I mean by that? So if I look at this equation, I have an equation for the Hamiltonian. The Hamiltonian, which so to say depends on x and y, it is not really a function of x or y. If you look at it, is actually in a differential operator. So let me say, rather than putting the argument as if it was a function, since this is a differential operator, let me say the Hamiltonian contains derivative with respect to x and y, and just want to put a pedix there to remind me. But actually, if I look at it, this is the sum of two Hamiltonian, which I will denote with small h, one which contains only derivative with respect to x, and that's this one, and one that contains only derivative with respect to y, this one. Now, this is obviously a very, 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 very specific situation, unusual situation, because normally the potential energy will mix x and y in non-trivial ways. So the simple decomposition of the Hamiltonian as a sum of one Hamiltonian that only considers acting on the variable x and another one that considers acting on the variable y is a very lucky and special case. We will encounter, nevertheless, more of these cases, at least in terms of approximation, where we will speak about mean fields much later on in the course. But at this very level, where we are still very preliminary in our excursion to quantum mechanics, we just notice this. And now I want to convince you of one thing. Anytime the Hamiltonian has this very beautiful property, and so if I want to write it more explicitly, I say Anytime the Hamiltonian can be split as a function of Hamiltonians which only contains a subset of variables, then the solution of the Schrödinger equation, which in 2 dimensions is x and y, and in more variables like many particles, so we have more coordinates, 1 for each particle or 2 for each particle, then of course you can generalize these to higher and higher dimensions. But let's stick to the 2-dimensional case. Then if I have a Hamiltonian split in 2 parts, then the solution can be written in the following way. Is the product of 2 functions, let me call it, I don't know, c of x, or let me call it even phi x for x, times phi y of y. Well, maybe the labeling is not the most fortunate one. So let me remove the x from here and say anytime the Hamiltonian is the sum of many Hamiltonians, let me call it H1 and H2, where this is H1 and this is H2. And this is for more than just one in case there are n. And each of these h, small h, is a function of a subset of variables. Then the wave function will be the product of 2 wave functions, one for each set of variables. And these functions are the solution of an eigenvalue problem. And the total energy associated to this solution will be the sum of the 2 energies. Now, this is a statement. So let me repeat the statement. Anytime the Hamiltonian factorizes into 2 parts, or in general, this can be generalized by many parts, and each Hamiltonian only acts on a subset of degrees of freedom that is different from the subset of degrees of freedom where the second part of the Hamiltonian act. And if you generalize, each of many Hamiltonians acts on a different subset of degrees of freedom. Then the total wave function can be written as a product of wave functions that solve the corresponding stationary Schrödinger equation. The first one solves the Schrödinger equation for H1. The second one solves the Schrödinger equation for H2. The product of this solution is the solution of the complete Schrödinger equation, and the corresponding energy, which is associated to this solution, is obtained by summing the corresponding eigenenergy. Now, if you go to more than 2 dimensions or 2 sets of variables, then you would have to say that the total wave function is a product for 1 to n of the wave function, and the total energy associated to the solution is going to be the sum of all the energy. Okay, this is a statement. I need to prove it. And in order to prove it, let me not take the most general case. Let me just take the simple case of 2 pieces. So let's do this. Let me act with H1. So let me take H acting on phi 1 of x, phi 2 of x. I want to take this. I want to see whether this is a solution of the Schrödinger equation for the complete system. Well, if this is the case, I must find here a number times phi 1 of x, phi 2 of x. If I do find something like that, it means that this particular product is a solution of the stationary Schrödinger equation. Okay, so let's go ahead. This is, let's go on, it's going to be H1, first Hamiltonian plus second Hamiltonian acting on phi 1, phi 2, right? Because of this definition. Now, by definition, H1 acts only on phi 1 and not on phi 2. So this is going to be phi 2, H1, phi1. Similarly, phi1, H2, phi2. Now I use the fact that phi1 is the solution of this equation, because this is going to be E1 phi2, and instead of this is phi1, and this is going to be E2 phi1 phi2, because I'm assuming that H1 phi1 is equal to E1 phi1, and H2 phi2 is equal to E2 phi2. So if I collect things together, I get this nice result, which is precisely what I was telling you before. So again, anytime my system is described by the Hamiltonian that is split into sub-Hamiltonians, each of which acts on a separate subset of the Josephine, my total wave function can be factorized as a product of wave function, each of which solves the corresponding Schrodinger problem for the corresponding subset of parameters. And the total energy, eigenvalue, are obtained by summing all possible things. Now, with this in hand, we can go back to our original problem. We have an Hamiltonian which contains a free Hamiltonian for box 1, which is the Hamiltonian along x, and the one along y. And I remind you that we know the solution of the corresponding Hamiltonian. Now we know the n, and this is going to be the sine root of 2 over L sine kn x, and root of 2 over L cosine of kx for n odd and even, remember? So the total wave function will be depending now on two different numbers, because, you know, I could choose a number n for the x and a number m for the y. So let me, you know, I have my wave function for the x box sine k m, and the one for the y box 2 over ly cosine k m y. So now my wave function in 2 dimensions does not depend on only one principal quantum number, like in 1D. It depends on two principal quantum numbers, nx and ny. And my total energy depends on two quantum numbers, because this is just h pi squared, h bar squared, L squared, and then I will get n squared plus m squared. So now I have a more intricate spectrum, but physically, why is it so? Why do I need two quantum numbers rather than one? Because you see, the quantum numbers n tells me what is the momentum state along the x-axis. And the quantum number m tells me what is momentum states along the y-axis. For instance, the ground state of this system would be one in which both wave functions, the one with respect to x and the one with respect to y, will be in their ground state. So this is n equal 1 and m equal 1, which will be basically, if I remind yourself of what this is all about, this will be like root of 2 over lx, 2 over ly, and then there will be a cosine of k1x and cosine of k1y. Well, this k1 and this k1 may be different, because k1 for x was actually pi over lx times n equal 1 in this case, while ky for K1 for y was pi equal Ly, the size along the y direction, and n equal 1, which is 1. So if I were to draw this on a box, I will get a density that is cosine along x and cosine along y, which basically amounts to having a density which is a cloud in the middle, maybe a little bit denser here, and less dense at the bottom. Another solution I could choose to consider, the next solution, there are two solutions. I could choose one in which, suppose Lx is larger than Ly, so Lx is larger than Ly, it means that the quantization energy in x are smaller. So if I take the first excited state in x motion, it's going to be smaller than the first excited state in the y motion. So the next energy level, phi 2, would be one in which n, which is the one referred to the x index, is equal to 2, and m, which is the one referred to the y index, is equal to 1. So there would be like 2 times 2 divided by Lx and y, sine of k2xx cosine k1 for y times y. And if I were to draw this, it would be something like, now there are two clouds, because remember the sign along, the x direction, the sign changes sign and is minimal in the middle. So the sign would be something like this. So my cloud would be like, more like this. That's it. Something like that. Okay? That's the probability density distribution sketch, and so on and so forth. And the more I get, I can go on and say n equal 1 and n equal 2. That will give me a first excited state along the y direction and the ground state along the x direction. Or I could get both excited states and so forth and so forth. I have more states, and which simply means that my particle can have components of velocity over x and y in the classical picture. And I could kick it differently in x and y to combine the energy in different ways. Okay, so this is allowing you to describe the particle in 2D, but we will see that this nice factorization of the wave function will come at handy also later on in the course when we will study particles, many particle systems with independent particle models. But this is, of course, much ahead in the course, and I'm not considering here. So I'd rather stop here for this very quick lesson. Have a goodbye.